This is mathheals.com, where you can find more links to math YouTube videos and computer science if you wish. And let's take a look at hypothesis tests for a population mean. Now in this particular book, they just have one particular type. Just hypothesis test for population mean, period. And other books have two different variations of it. One where sigma is known and one where sigma is not known. So keep that in mind if you're watching this and you're using a different book. I'll kind of tell the difference on the calculator, so that if you are using a different book, you'll see it. The requirements for this: the samples obtained using a simple random sampling or from a randomized experiment. Sample has no outliers, and the population from which a sample is drawn is normally disputed, or the sample size n is large. N is greater than or equal to 30. And the sample values are independent of each other. Now we're going to assume all these are true for the examples I made up. I'm not very good at making up examples, so we'll run with these assumptions, even if it doesn't say it. Now this is the classical approach using the TI-83-84. We write down a shortened version of the claim, come up with a null and alternate hypothesis. H0 always has the equals part on it. Step 3, see if the claim matches H0 or H1. Step 4, draw the picture and split alpha into the tails. Step 5, find the critical values, t-distribution table. And then step 6 is find the test statistic, t-test. If test statistic falls in a tail, we'll reject H0. If test statistic falls in the main body, we'll accept H0. And determine a claim based on step 3. Now I like to use the word accept and reject, but most books will use do not reject. Accept is kind of an incorrect word, and this is the example I always give. I had a student one semester. She's an art major, and she made 7 or 8% in every test. Did poorly. You have to leave a lot of them blank to get 7 or 8% on one of my tests, or you have no clue what you're doing. She came in for the final exam. She got 100% on the final. Scored 25 out of 25. Well, I think what happened is she came in with the answers on her calculator. Somebody from a previous class had taken the test and came in, and everybody at the college uses the same departmental final exam. Well, from then on, I started coming up with my own. I randomized the numbers because the odds of her making 25 out of 25 when she's scoring 7 or 8%, the probability is just super low. It just doesn't happen. She cheated. I can't prove it, so I don't accept her innocence, but I do not reject her innocence, because maybe it's possible. Maybe she spent the last 2 or 3 weeks studying every second of the day. You don't know. That's why accept is a pretty strong word. Instead, you say do not reject H0. Now, I find students click better if I use reject and accept, so that's what I'll stick with. Let me work these problems, then I'll talk about the two different types. Note here, practical significance refers to the idea while a small difference between the statistic and parameter stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or be considered important. I did a statistical study one time based upon actual data, something I wanted to determine, and it showed that there was a significant difference. But when I actually started looking at the numbers, it's just like, well, really, there's not much of a difference here. So that's what it's referring to. Is even though it may statistically show it's significant, in reality it doesn't make much difference. Well, let's take a look at our first problem here. It says the mean amount of fluid in a bottle of lens cleaner is 59 milliliters. I was getting bored, trying to think of, or drawing a blank. I was thinking of a test question, so I had the lens cleaner sitting here on my desk, so I pulled that from that. Okay, so the mean amount is 59. Well, that didn't say anything about a sample, so that's talking about mu. Researcher believes that the mean is actually lower than that. That sounds like a claim. So lower than the 59. 15 bottles are sampled. N is 15. And the mean is found to be 58 milliliters. X bar will be 58. With a standard deviation of 1.2 milliliters. So that's S. Now these are sample values. That's why I used X bar and I use S. Because it's referring to the 15. It says test a claim based on this information that alpha is equal to 5%. So alpha is equal to 0.05. Okay. Find it somewhere here. There's my PowerPoint. Step 1. Write down a shortened version of the claim. We did that. Step 2. Come up with a null and alternate hypothesis. H naught always has equals part on it. Actually, the only symbols you can put on H naught are less than or equal to, greater than or equal to, or equal to. The only symbols you can put on H1 are less than, greater than, or not equal to. Now lower than, that implies less than. And so come up with null and alternate hypothesis. We're talking about the mean, which is mu. Why are we talking about the mean? The mean amount is 59. Researcher believes the mean is actually lower. It's talking about the mean. So that's why it's mu. Well, less than would go here. That's the only place you can put a less than. And if this is less than, this has to be greater than or equal to. These are opposites of each other. Now, our current textbook will always put an equals here. One of our older ones did it in this form. I like this form better because if these are opposites of each other, if you reject this and you accept this, if you just put an equals here, then that's technically not true. Step 3. See if the claim matches H naught or H1. Well, this matches H1. Step 4. Draw the picture. Split alpha into tails. Less than on H1. Less than on H1 is this one right here. It says left tail. So put a left tail. This right here is our critical value. Now it says split alpha into the tails. Alpha is 5%. We only got one tail, so we'll put the entire 5% there. And I'll put 95% here. It all adds up to 100%. Now it says for your critical values, use a t-distribution table. Well, for the t-distribution table, we need degree of freedom, which is n minus 1. Well, n up here is 15, so we've got 15 minus 1, or 14. So we'll look it up in our table. Now what this should say, unfortunately it doesn't, but it should say area in one tail. Sometimes you don't even have a right tail. We don't have a right tail here, do we? So it should say area in one tail. Well, this is 0.05, so I'm going to look in the column for 0.05. And our degree of freedom is 14, so I come over here left-hand side, I'm looking for 14, which is right here. So we got 0.05 and 14. So 0.05 and 14, we get 1.761. Now, if your critical value, and this only applies on a t-distribution table, so don't use it everywhere. Definitely doesn't apply on the chi-square. In your t-distribution table, if your critical value is on the left side, it's negative. If it's on the right side, it's positive. So that's a negative 1.761. Now for our test statistic, it tells us to use t-test. So let's go to the t-test. I'm going to press stat. I'm going to right arrow over to test. And I want down arrow to t-test. It got down arrow, didn't I? There it goes. Now when it comes up, there's data and there's stats. If you're given raw data, you want the first one. If you're given summary statistics, you want that one. If it's not already highlighted, then right arrow over to stats, put your flashing cursor in stats, and press enter on it. Now mu naught, that's always going to be the number off of our claim, which is 59. So I type in 59. X bar, we said was 58. S is 1.2. N was 15. And the symbol on H1 is a less than. So you want to right arrow over, put your flashing cursor on the one that's a less than, and press enter if it's not already highlighted. Then down arrow and do enter and calculate. Now the T equals is your test statistic. So for our test statistic, our T equals negative 3.23. Start out taking the 2 decimal places. I don't know if that's enough. Every problem's different, so you really can't say. You just have to see if it's real close to your critical value, because you need to decide which side it falls on. This is the number line. Here's negative 1.761. So negative 3.3, number line-wise, would fall over here. So it falls in our tail. Okay. If test statistic falls in a tail, it says we reject H naught. This is our conclusion. So falls in the tail, reject H naught. Now H naught and H1 are opposites of each other, so if I reject H naught, that means I'm going to accept H1. Now our claim matches H1, so whatever we say about H1 is what we're going to say about our claim. Since we accepted H1, that means we'll accept our claim. Okay. Let's look at our next problem. I'm kind of surprised on that one. I mean, obviously 58 is less than 59, but I wasn't sure with the standard deviation what it would do. Because 58 is fairly close to 59. You know, this would be like an example. You know, here you see we accept a claim that is statistically significantly lower. But for practical purposes, if we're talking about ages of, or even not even ages, just if you think of milliliters in the bottle here. My bottle I got in my hand here is a pretty small bottle. Well, my eyes are bad. I think it says 2 fluid ounces, so not much at all. So there's really not much difference between 59 and 58. So it's not really significantly lower in a practical sense. That's what that note's talking about. Okay, number 2. I'm still on my bottle of lens cleaner. That was on my desk. It says its mean is 59. Researcher believes that the mean is different. Sounds like our claim. Different than 59, which means it could be less than, could be greater than, so it's just different. 35 bottles are sampled, so N is 35, and the mean is found to be 63. So X bar is 63, with a standard deviation of 2.3. So S is 2.3. Now these are X bar and S sample because we're talking about the N. Test the claim based on this information that alpha is equal to 1%. Okay. Let's go through our steps. Step 1, write down a shortened version of the claim. Did that. Come up with a null and alternate hypothesis. Different than, that symbol's a not equals to. Not equal to goes here. If that's not equal to, then equals is up here. 59. Step 3, see if your claim matches H naught or H1. Different than not equal to, that's symbol we put here. So it matches H1. They don't always match H1. They do a huge amount of time, but don't be surprised if one of your problems matches H naught. Step 4, draw the picture. Not equal to on H1 says we're going to have two tails. So we're going to have a critical value here. We'll have a critical value here. Now we want to split our alpha into our tails. Alpha is 1%, 0.01. If you take that and put in your calculator, 0.01 divided by 2, you get 0.005. Like that. Now if 1% is in the tails, then that means we have 99% in the main body. Step 5. Find our critical values. Use the t-distribution table. Remember, we need our degree of freedom, which is 1 less than n, so it would be 34. And let's go look it up. Okay. Area in a right tail. Remember, that should be area in one tail. Well, area in one tail is 0.005. So we're looking in this column, and we're looking for degree of freedom of 34. So 34. Shouldn't have had it so far down. Which one is it? Fourth from the right. 1, 2, 3, 4. Yeah, fourth one. And 34. 2.728. My eyes aren't getting off, which they do. 2.728. Let me double check that. Yeah. Now we got two critical values here, so they're both going to be 2.728. Remember, with a t-distribution, if your critical value is on the left side, it's negative. If it's on the right side, it's positive. Well, let's find our test statistic. We're going to use t-test for that. So I'll press stat, go to tests, choose t-test. We're given summary statistics again, so I want stats highlighted. If it isn't already highlighted, right arrow over to it, press enter on it. Mu naught, that's always a number off your claim, which is 59, which is already there, but X bar, 63, S, 2.3, N, 35, and the symbol on H1 is a not equal to. So our flashing cursor is on not equal to right now. I'll go ahead and press enter on it. And that way it'll change the highlighting to it. And then I'll down arrow to calculate and press enter. Now the t equals is our test statistic. So 10.29. Okay. Here's the number line. Here's negative 2.728. Here's positive 2.728. 10.29 would fall over here. So for a conclusion, if test statistic falls in a tail, well, it falls in the right tail, doesn't it? It says we reject H naught. So we reject H naught, which means we accept H1. And since our claim matches H1, whatever we say about H1 is what we say about our claim. So we'll accept our claim. And I made this one pretty significantly different then. See, it was 59. I made it 63 because I wanted to, for us to accept this claim. Even though we accepted this one up here. I wasn't sure when I made up these numbers. When you make up numbers like that, you think, okay, well, it's pretty close. But you just have to plug it in and see what it gives you. Let me save this. Then we'll look at our last problem. Okay. What am I doing here? There. Yes, hypothesis test for a population mean. Classical approach. TI-83-84. Yeah, I'll just say TI-84. page 01.pdf. Yeah, looks good. Okay, let's look at our last problem. Okay, mean amount of fluid in a bottle of pop. I've been drinking pop, in case you're wondering. Is 16.9 fluid ounces. So that's our mean. 16.9. Kind of weird. I wonder why they didn't put 17 in there. Oh, it's 500 milliliters. That's why. Okay, a researcher believes that the mean is more than that. Believes more than that. So that implies more than 16.9. 10 bottles are sampled, resulting in the following data. N is 10, and then we got these numbers. Test a claim based on this information that alpha is equal to 10%. Okay. Here it is. Write down a shortened version of the claim. Well, we did that. Come up with the null and alternate hypothesis. These are mu's. More than. That symbol is greater than. Greater than goes here. 16.9. If that's greater than, this will be a less than or equal to, because they're opposites of each other. Now step 3 is see which one it matches. This is a greater than, this is greater than. It matches H1 yet again. Greater than on H1, picture-wise. Greater than on H1 is right here, which means right tail. It says split alpha into the tails. Alpha is 10%, so I'll put 10% there because we only got one tail. If that's 10%, this has to be 90%. Step 5, find your critical values. Use the t-distribution table. Well, to use that table, we need our degree of freedom, which is 1 less than n, which is 9. So let's go look it up. Okay. Now the area in one tail is 10%. So I come here to the 10% column. I'm looking in this column. Our degree of freedom is 9, so I come over here to 9. And 10%, the intersection of those would be 1.383. If my eyes didn't get off. 10%, 9, 1.383. Okay. It's on the right side, so it's positive. Now for our test statistic. Our sheet tells us we're going to use t-test. If I go to t-test, though, something's wrong. If I press stat, go to tests, down arrow to t-test, and press enter. We don't have all this information. But we do have raw data now, don't we? Now, if you press the left arrow and put your flashing cursor on data and press enter, it'll kind of guide you what to do. See what it says? List, L1. Well, that implies put your numbers in L1. So I'm going to do a second mode to exit out. And I'm going to go into stat, go into edit, and I'll press delete a few times to get rid of those numbers in there. Okay. Now our numbers for this problem are right here. So we've got 16, 16.1, 17, 17.5, 17.2, where am I at? 17.5, 17, 17.5, 16.3, 16.7, and 18.7. Okay, 18.7, 16.7, 16.3, 17.5, 17.17, 17.2, 17.5, 17, 16.1, and 16. Now, the 18.7 might be considered an outlier because it's pretty far away, but I put that in there so that if I show this by hand, I'm showing it on a calculator now, but if I were to show it by hand, the numbers work out a little nicer by me fudging the numbers like that. Okay, we got our numbers entered. Do a second mode to exit out. So now we're going back to Stat, going to Tests, and I'll go down to T-Test. Okay, data is when you're given raw data, which is already highlighted. Now, mu naught, that's always going to be the number off of your claim. We put 16.9 there. So 16.9. List, we put ours in L1, that's fine. Frequency, always leave as 1. The symbol on H1 is a greater than. So I'm going to right arrow over to the greater than and press enter. Then down arrow and press enter and calculate. Okay, so our test statistic is equal to 0.39. Now here's a number line. Here's 1.383. 0.39 would fall over here. So our conclusion, our test statistics is fallen in the main body. It says if test statistic falls in the main body, you accept H naught. Which means you reject H1, because they're opposites of each other. And our claim matches H1. So whatever we say about H1 was what we say about our claim. So we'll reject our claim. That was interesting. I didn't know how that one would go because I just made up the numbers. But anyway, that's how you you do that particular one. So let me save this page. Actually, maybe I'm lying to you. I don't want to save it yet. Let me talk a little bit about differences in books. It's kind of frustrating, I know. Now, in this particular book, we use the t-tests and we use t-distribution for any of the mean. But different books do different things. Some of them based upon whether sigma is given or not. If sigma is known, then your critical value, you're going to use I and V norm to find it, and your test statistic will be z-test. Now, if sigma is not known, then your critical value is the t-distribution table, and your test statistic is the t-test. So, like I say, for this book, they simplified it a lot, and just there's one mean, and we use t-distribution table and t-test for everything. But if you got a book that has both of those, that's the differences between them. Now let me save that. And let me stop the recorders. There we go.